Why do we say that the true giants of the universe have actually been hiding right under our noses? Those forces that make stars shine, planets orbit, and galaxies spin on the ultimate stage of the cosmos might not even qualify as supporting roles. We've always assumed that the twinkling stars in the night sky, the majestic galaxies, and the colorful nebulae are the most powerful entities in the universe. After all, they are visible, tangible. Telescopes can capture their light. Formulas can calculate their mass. But here's the cruelest truth of the cosmos. Everything we can see, combined, makes up less than 5% of the universe's total mass. The remaining 95% is controlled by invisible overlords we cannot see or touch. Yet who dictate the fate of the entire cosmos? Today, I'm taking you into space to uncover these mysterious cosmic forces. One thing we must understand: these forces aren't invisible because they're too far away, nor because they're too small. They are like masters of invisibility, neither emitting light, nor reflecting it, nor even interacting with electromagnetic waves. No matter how advanced our telescopes, or how sensitive our detectors, they leave no trace across the spectrum. They are fully cloaked in darkness. But don't be fooled by their low profile. Like hidden masters in a martial arts epic, these unseen guests are the most violent, extreme sources of energy in existence. When two black holes stage a cosmic showdown in the depths of space, they spiral toward each other at nearly the speed of light, collide, and merge. The energy released in that moment equals the combined brightness of hundreds of trillions of stars. This colossal cosmic explosion is what we call gravitational waves. These hidden forces don't just influence local events, they hold sway over the destiny of the universe itself. For most of human history, we've stumbled blindfolded through the garden of the cosmos, mistaking glowing celestial bodies for all that mattered, and dismissing anything that didn't shine as non-existent or irrelevant. Yet as science advanced, we came to realize that while light is an incredible tool for knowing the cosmos, it is not the whole story. Just as we cannot rely only on sight and ignore the gift of hearing, the universe speaks another language, and it's been waiting for us to listen. That language is gravitational waves. Gravitational waves are like the breathing, the subtle tremors of the universe. They've existed since the dawn of time, but only recently did we begin to notice them. Among all events that generate gravitational waves, black hole mergers steal the spotlight. Black holes are among the most mysterious cosmic objects, remnants of massive stars collapsing under their own gravity. They are unimaginably dense, so massive that not even light can escape their grasp. A black hole is a true abyss of gravity. Once matter crosses its boundary, it is lost forever. But black holes, too, face monumental challenges. What happens when two of them meet, each several times the mass of the sun, locked in a spiraling dance, spinning faster, drawing closer, until finally colliding into one larger black hole, and then slowly settling? The tremors from this violent event are staggering. The released energy ripples through spacetime at light speed. After decades of theory, calculations, and relentless attempts, humanity finally heard these waves a few years ago. It was as if Einstein's century-old dream suddenly became reality in our time. But even before we truly heard the universe whisper, clues were everywhere. Strange pulsars slowing down, stars disappearing, galaxies wobbling, objects behaving as if pulled by invisible gravity. At first, we had only imagination and conjecture. We invented terms like compact objects, stellar remnants, black holes, words that sounded like science fiction, and for years, we weren't sure if they were real or simply errors in equations. But as evidence mounted, we began to see the truth. Some binary systems in the Milky Way weren't single stars at all, but pairs of black holes orbiting each other, destined to lose energy, spiral together, and ultimately merge. More astonishing still, these cataclysmic events have been happening for over 10 billion years, since the birth of the universe, during galaxy formation, and even now, they continue unabated. We just couldn't sense them, because they emit no light, leave no obvious traces, only faint ripples in spacetime. So what exactly are gravitational waves? Why are they so extraordinary? Simply put, gravitational waves are ripples in spacetime itself. Picture tossing a stone into still water, and watching the ripples spread outward. The universe does the same thing. Its ripples are gravitational waves. They spread at light speed, distorting space along their path, though only by tiny amounts, imperceptible to humans, but detectable by the most sensitive instruments. Over a century ago, Einstein predicted their existence, purely from his equations of general relativity. In 1916, he realized, if mass accelerates, it must disturb the gravitational field, sending waves outward like ripples. Even Einstein doubted they could ever be detected, since they are so faint. It takes cosmic catastrophes, black hole collisions, neutron stars whirling at near light speeds, or supernovae, to create detectable electrical ripples. The beauty of gravitational waves is that they are ultimate messengers of the universe. Unlike light, which can be absorbed, bent, or scattered, gravitational waves pass straight through stars, through galaxies, untouched and unbroken. This makes them an incredible tool. They allow us to trace cosmic events directly to their sources, without distortion. And gravitational waves come in many forms, classified not by frequency, but by the shape of their signals. Compact binary coalescence, CBC, signals, the most famous, most observed kind, from merging pairs of black holes or neutron stars. These spirals and collisions create signature waveforms that explode across spacetime. Burst signals, short, intense, and unpredictable, like cosmic bombs, supernova or prime candidates. Continuous waves, CW, steady, rhythmic signals, like a cosmic metronome, often from a spinning neutron star, with slight imperfections on its surface, producing endless ripples. To detect them, scientists built machines that seem lifted from science fiction. The US LIGO Observatory, Italy's Virgo detector, and others. Together, they pinpoint signals, confirm results, and eliminate false alarms. If a wave is recorded in multiple locations, at the right time, it is undeniably real. And what's the point of detecting them? What makes them so special? For one, they directly confirm Einstein's prediction, a monumental milestone for physics. They allow us to test relativity with unprecedented precision, to study the most extreme cosmic events, black hole mergers, neutron-star collisions, supernova explosions, events nearly invisible in light, become loud and clear in gravitational waves. When two black holes merge, the energy released is equal to billions of suns exploding simultaneously, enough to shake the fabric of spacetime itself. If strong enough, gravitational waves could even alter spacetime structures in ways we cannot yet predict. They also offer clues about dark matter, dark energy, and supermassive black holes, phenomena that could rewrite our understanding of the cosmos. In theory, if an ultra-powerful gravitational wave passed Earth, it could subtly distort space and time itself. That's why gravitational wave research is revolutionizing our grasp of the universe. As detection technology advances, gravitational wave astronomy will unveil a universe more dazzling, complex, and mysterious than ever before. It will deepen our understanding of cosmic origins, evolution, and structure. And perhaps soon, we will use these ripples, this ear of the universe, to hear the very first cry of creation, to uncover the secrets hidden in cosmic darkness, to solve humanity's oldest mysteries, and to open a brand new era of cosmic exploration.